So good morning. So today we are going to have a session on these points. We will discuss about different types of elements. This is one thing, and another one. What does that basic functions that is also called as a shape function for the element, which talks about the variation of your field variable with uh, what are the x, y, z coordinates. We are going to discuss about 2D element also 3D elements and all this. And also we are going to discuss about convergence criteria we normally use in this and what kind of nodal unknowns are to be determined. Those points also we'll cover in this particular presentation. So when we look into the 1D element, it is a typically spar element or beam element, truss element, bar element. It is all comes under 1D elements. Okay, all this comes under a 1D element. When we are going to choose a nodal point, if I consider in a structure like this, so this is my typical structure. I want to put up on a nodes at different locations so that I can define elements on this. Okay, so when we are going to decide on a node, so first criteria in this, so you can decide this may be in a material aluminum, this may be in a steel material. Okay, this is nothing but a junction for it. So you can put up on one node for this because this is going to separate from these two materials and it will be seen separately out. Another one, junction of two different materials, two different cross sections. This is what on a different cross section. This is having in a smaller area and this is having in a larger area. This is what on a junction. And at that point, I need to put the nodes. Another one, whenever I'm going to put up on a load, if I'm going to apply a load somewhere here, so I need to consider node at this point. This is what the way we can create a mesh for entire model. So that is what the way we look into the elemental conversion or meshing kind of thing. If I put up a force at this point, so obviously I need to consider a node for this, and then I can now convert this into one node, one element, then second element, then third element, and then fourth element. And this is I'm going to fix it. This is what on a force I'm going to apply. This is what on a material junction, which talks about this. Then again, material cross section change. Then this is another force I'm going to apply it. And this is nothing but a final point. So this is the way you can create a mesh for any kind of an element. This kind of a meshing is quite easily done using any FEA solvers, maybe answers or any kind of an FEA solver which will take care of this easily. And that's the reason. For this purpose, there is a certain algorithms are created. Algorithm, what this algorithm does, these algorithm will identify the locations where you have applied forces on model, and based on that, it automatically put the nodes at that particular location. And sometimes in some of the FEA solvers or FEA tool, you might have seen some kind of a warning or kind of message which will say, "Okay, I want to convert the load points into nodal point or something." So this is what happens. So another one, in 1D element, axial dimension is very large. If I consider in a axial dimensions, if I consider in a bar and I'm going to apply the force on the bar, what will happen? Deformation in this direction is a large compared to radial direction. Already this point we have discussed, and that's what large compared to the cross section. And the load is assumed to be uniformly over the entire cross section. What are the cross section? So I may be applying at the center, but it is assumed that this load is completely applied on the entire surface. And what are the cross? That is what it happens. Then displacement is considered to be a function of x. X is nothing but a coordinate. This is my x coordinate. And what are the deflection? You are going to do it. So this u is nothing but a function of x. That is what in 1D element. Similarly, you can look into the 2D element. This function will become an u is now function of x and y coordinate. If I consider an 3D element, I can have a function of x, y, z, and then theta x, theta y, all this theta z. These are the all variables will be taken into account. So stress and strain also assumed to be uniform over the entire cross section. If my cross section is somewhere in this fashion, and whatever the stress, if I'm having this is one single element, stress at this location, and this location, all the values of the stresses will be the same in the single element. That is one thing. It is assumed. This is what a technique. This is what the way we take this FEA for an analysis. So if you look into the elemental shapes, there will be a one-dimensional element. One thing. Then there will be a two-dimensional element. Then there will be an axisymmetric element. Then 3D element. Axisymmetric elements, maybe plane stress also will be there. Plane stress, then plane strain is also there. Likewise, we do it. What is the reason for this? This is basically reason for converting. This is nothing but a conversion of 3D to 2D. That is what in a 3D model, and you want to convert into 2D model. So that is what in a basically first intention. Why we are doing? If I consider any point in the space, will have a 6 degrees of freedom. That is x, y, z degrees, x, y, and z degrees, and rotation of each one. So likewise, I will get in a 6 dy for in a single point in the space. Means I will get in a 6 equations for in a single point into this. And if I have an element of a 3D element, if I consider a brick element or kind of things, altogether it will have an 8 nodal points onto this. These are the 4 nodal points on front face, then another 4 nodal points on back face. Likewise, 8 nodes, 8 noded single element. And if each node is having a 6 DOF per node, then total number of equations becomes 48 numbers. And then for a single element, you need a 48 by 48 bigger stiffness matrix, and you're going to solve. Then it becomes too much complicated if you go for more and more kind of elements and nodes and kind of things. So to avoid that, some of the cases where I can consider only 1D analysis or one dimension deformation, one direction deformation I want to analyze, one direction temperature I want to analyze. So in that case, this will be much more helpful. So to converting 3D into either 2D or 1D kind of. So for that purpose, these are the concepts is mostly used to convert 3D model into a 2D model. One concept is an axis symmetry. Consider an element with an axial symmetry, and instead of doing an entire complicated analysis, you can only reduce it to maybe a 3 element, 4 element, or 3 element or kind of thing, and it will reduce the number of equations. That is what an advantage we can get it. Similar fashion, you can get an advantage in plane stress condition, plane strain condition. So if you want to analyze an entire model in all the three directions, so in that case, this 3D analysis is on but obvious kind of a case. We can go ahead with that. So if you look into the first 1D element, 1D element means each node is having only 1 degree of freedom, 1 D or one node. That is what basically called as a 1D element. If I have only two nodes, so if the deformation of this node is an U1 and deformation of this node is U2, I will get only 2 points to map on the displacement point. So obviously these 2 points will be joined with an only straight line, and that equation is typically A0 plus A1x. Maybe in a polynomial also you can have on this equation like an mx plus c or something. That is what on a straight line. That's what it is called as a linear elements. Okay. because it shows a behavior of deformation of an element in linear fashion. That's what, or it follows in a straight line or linear equation to represent that behavior. So what is called as a linear equation. If I include one more node in between it, okay, this is my one DOF and then second DOF, then three DOF. Means I will have here I will in linear element I will have a 2 by 2 matrix and for stiffness matrix A is 2 by 2. So if I look into the 3D element, okay, in 3D element, what it happens, I will have a 3 degrees of freedom. So I will have a deformation U1 here, then I may be having a U2 here, maybe having a U3 here like this. So obviously, if you are going to connect these 3 points in the space, so that will be in a kind of on a curve, and that curve is called as a quadratic equation. This is what a quadratic equation, and it is represented by equation y a0 plus a1x a2x. The power is in a 2. That's what also called as in a second order polynomial is. So then this type of element is called as in a quadratic element. And this quadratic element will have a stiffness because we have a three nodes and each node is having a 1 degree of freedom. So obviously my matrix becomes a 3 by 3 matrix. So if I increase one more, is ultimately in this linear element, my equation is y is equal to a0 plus a1x. Okay. In this case, my equation is y is equal to a0 plus a1x plus a2x squared. Then if I increase one more node, I will have a one, two, three, four nodes into it. So obviously my stiffness matrix becomes 4 by 4 for a single element. And my equation for this particular behavior of displacement will have an y is equal to cubic equation, that is a0 plus a1x plus a2x square and then a3x cube like this. This is nothing but the highest order I am getting it. That's what this is what it is called as a cubic element. So similar fashion, I can go on increasing the node in between the two nodes and I can go on increasing the order of the polynomial. This type of analysis is called as a p-type because you are p-type analysis or polynomial type. So if you want to get a more and more accurate solution for any kind of a problem, there will be two ways. One is I can decrease the elemental size. Elemental size, I can concentrate on elemental size. And another one, increase the order of polynomial. Order of polynomial. Okay. In increasing the order of the polynomial, what it indicates, increasing the order of the polynomial indicates, so you're going to have an increasing this x power, that is x1, 2, 3, 5. So that's what this type of analysis is called as a p-type analysis. And in decreasing the size of the element means we are keeping this element as in one single, maybe in a linear element, and you are going for more number of elements. This type of analysis is called as an H type analysis. And this will, both methods will lead to a better accuracy. Okay. But if you are dealing with a P type of polynomial, I need to go for more and more higher order polynomials. That is one thing. And it will give a better result with a less number of elements. That is what we get. But in this case, for a linear element, I can go on reducing the size and increasing more number of elements, which will lead to better results and that is what see it. So this is what the way you can look into the 1D element. So this is 1D within a 2 degrees of freedom, 1D within a 3 degrees of freedom because we have 3 nodes onto this, 1D with 4 degrees of freedom because we have 4 nodes in a single element, and we'll get here it is in a first order polynomial, then it is here it is in a second order, and this is third. So this is what the way it is called p-type approximation, higher order polynomial approximation. So if you look into the 3D, the 2D element, we'll just move towards 1D to 2D element. So if I have on a plate like this, I want to convert that plate into an elements. I want to mesh it. What is the way we can do it? I can now convert that into an mapped mesh. This is what it is called as a mapped mesh. I can now have an convert this into an triangular shapes. Like this, I can go on converting into triangles. Like this. Okay, I can go on increasing the more triangles and kind of thing. This is what in a basically first step. First shape is triangle. This triangle may be an of any shape, maybe an all the size are uniform, maybe an two sizes are same, maybe a rectangle, triangle, any shape we can get. But the thing is that which shape suits to that particular environment or that particular behavior. So that is what we need to take. So here, so typical a single element is taken into account, and each this for a typical triangle there will be three vertices, okay, and each vertices there is a possibility it will move in x direction as well as in y direction. That is what it happens. So this is what on a point it can move in x and y. That's what each node will have on a 2 degrees of freedom. That's what it is called as 2D webs or 2D, that is a two-dimensional analysis. Okay, so there will be a two-dimensional analysis in this. If I consider three nodes onto this, just imagine there is this is my x-axis, this is my y-axis, and this is my deformation. Maybe I defined an element in this fashion. Okay, so this node will have a deformation, maybe an u1 here, maybe deformation u2 here, and this may be having an a u3 here. Okay, so when I join these three points, I will get in a certain shape, and that shape is called as a displacement field or displacement field. So this will have an equation. This u is now varying with respect to x and y, and this is called as a shape function for particular element. So this is what on a shape function for a triangular element. Now, when we are going to define this shape function, there will be a certain criteria by which we can define it. Why it is kept into the criteria? The reason that how this variation is there. So how this whether that particular variation is linear, then quadratic, or kind of things. That is what it is called as a shape function. So if you look into this element, there is one more term mostly it is used, that is a constant strain triangle. If I consider an element u is equal to u is nothing but a now function of x and y, I can have a single linear element, that is a1, a0, a1x, and a2 y. That is what x and y are two variations. So power of this x is 1 here and y is 1. That's what it is called as a linear. Okay, and if I want to convert that linear or what are the displacement into the strain, so you know that strain is nothing but what strain is equal to change in the length, change in the deformation, or deformation divided by what are the length. That is what it is called strain. If I look into this du by dx and du by dy, these are the partially depend on x and partially depend on y. If I taken a first derivative for this with respect to x, it becomes this is a constant, it will be 0, and even I will get, and then I will get an a 0 because this also we need to take constant, and we that constant derivative is 0. So then here it is in a 0, then again 0, then it becomes an a 2. So if I consider du by dx, which is equal to a1, and this is nothing but a constant. Okay, then du by dy is again constant, that is a2, and that's what it becomes in a constant strain triangle because it behavior of this particular function, this function is nothing but which represents a strain over the entire element. Means if I am going to determine the strain at this location in or this location or any location, I'll get the same value in x and same. So that is what the way we can look into this. This is what that's what it's called as constant strain triangles. Okay. If you look into the particular functions like u, this is what the two equations you can get when one is in x direction, other is in y direction. This u is nothing but represent the deformation in x. V is represent the deformation in y direction. So now, if I consider this as an function, this is what it is called as a displacement function, f of x, y, or whatever those. Okay. And if I have a nodes, three nodes, so obviously, if I'm going to join these 2 points, obviously that will be in a one equation, that is what a linear equation. And if I take a derivative of this linear equation, I'll get a constant. So this is the reason this represents in a constant strain triangle, and which will help us to know how much strain is there in each and every element. So this is what basically a fundamental property requirement in whenever we are going to define any polynomial into the polynomial for elements in 2D or 3D. So we'll now move towards the next part, and if I increase one more node in between it, okay. So you can just look into one piece. This is my x-axis. This is my y-axis. Okay. I have a triangular element like this. These are the four vertices for this, and I'll consider one more node in between it. Okay. These are the internal node, I can say. So this I will get one deformation. This is another deformation. These are the three deformation. I will get one more deformation at this location, another one, and third one. When we are going to join these 3 points, it will create in a certain shape. That is what it is called as a quadratic shape. And that's what behavior of the displacement field. This is what a displacement field is. Uh, is a quadratic behavior. That's what these elements are called as a quadratic element. Or also, if I taken a derivative of this, now you want to convert that into u as a function of x and y. My equation becomes an a0 plus a1x plus a2x y, then a3x square, then a4 y square, and a5 xy. So power of this x and y is a square. So that is what it happens. So that's what this behavior is. This equation is typically a quadratic equation. Okay, and that's what it is called as a quadratic element. It is called. If I take a derivative of it, du by dx or something, similarly, you can take a derivative in y direction also. You can represent in v, x, y something, but different constants into this. So du by dx, if I take a derivative of this will become 0, then this is plus a1, then this becomes 0, then this becomes an 2a3x, then this is 0, this is a5y. Okay, so now if I write it this equation, a1 plus 2a3x plus a5y. So this equation, power of this x is a 1 here, and that's what this deformation, whatever the strain is nothing but called as a linear strain. Strain is linear in this case. That's what this is called as a linear strain triangle. Linear strain triangle. Because it represents the behavior of the strain in linear fashion over the entire element. Means in previous case you observed that strain at any of the location in the element was in a constant. That is a fixed value. But in this case, that elemental for this case and this case, whatever the variation will be in a straight line something. That is what it happens, and that is what it is called as a linear strain. Similarly, if I increase one more node on the edges and one node in the center of this, what will happen? Obviously, I will get in a 4 points and I will get in a cubic equation. Then this type of element is called as a cubic element. Okay, this type of element is called as a cubic because equation is cubic kind of a behavior. U becomes a cubic equation that is a function of x and y, and it is a cubic in nature. And if I take a derivative of cubic equation, I'll get a du by dx. I'll get a somewhere square or something. So that is what, and it is a quadratic behavior, and that's what it is called as a quadratic strain triangle, or also it is called as a QST. Also, it is a cubic displacement triangles. So if I increase one more, just to look into this. So obviously, here the behavior is on a fourth order. Displacement behavior is a fourth order. Displacement is fourth order, and then strain is nothing but in a cubic. So the third order, I can say, and that's what it is called as a cubic strain triangle. Similar fashion, I can go for fifth order, sixth order. I can go for such n number of orders, and I can define the triangle cases. Okay. So now we look at another part as one is the way by which we can measure this entire model with triangular shapes. Another way by which we can do it is rectangular shapes. So this is nothing but a typical shape. Rectangular element, what it happens, I will have four corners of the rectangle, and these each corner will have 2 degrees. Okay. So in this case, stiffness matrix, each node is having 2 DOF. Each node 2 DOF. I have 4 nodes, then total DOF. Total DOF becomes 8. Means my stiffness matrix here 8 by 8. So this is what on a bigger matrix. If we look into the triangular shape, what it happens, I will have a simple triangular element, that is what on this triangular element. Then in this case, I have 3 nodes. Per node is 2 degrees of freedom. So my stiffness matrix becomes 6 by 6. Here, in this case, in quadratic, I have how many nodes? 1, 2, 3. Altogether, 3 plus 3, 6 nodes. 6 into 2, it becomes 12, and my stiffness matrix becomes 12 by 12. So similarly, I can go on increasing that number, or bigger and bigger matrix sizes will higher order. So in the same way, here it is in rectangular. In rectangular, for linear kind of an element, this is what on a linear element, okay, which is having a stiffness matrix of size 8 by 8. Okay. So similarly, there is one more concept you might have learned in numerical methods, that is Lagrange interpolation. In this Lagrange interpolation, so there will be we are going to join the points to model points. Interpolation, and there is a basically very nice difference between interpolation and uh, curve fitting. In interpolation, what it happens? So I have given in some points into the space, maybe an x and y there. I'm going to join these points through this line. So if I have 3 points, I'll get in a quadratic equation. If I have 4 points, I'll get in a cubic equation. But in case of curve fitting, we will first of all decide what kind of a curve you want to fit it. Maybe in a straight line, maybe a quadratic or something. So these points means I'm going to join this. I'm not going to join the curves or join these points, but I'm going to create an approximate line. So that is what it is called as a curve. Okay. But in this FEM, what we are doing, we are going to use an interpolation, not an curve fitting. We are not using an curve fitting into this, but we are using an interpolation. In this interpolation, you might have learned about linear interpolation, quadratic interpolation. But along with that, there is one technique is called as a Lagrange interpolation. In that case, what we can do, define, if I go on increasing the order, or I want to increase the order, I need to just include few more terms into it. So that is what the way this Lagrange interpolation functions works. And this is the different triangles through which it is represented. So this is one way, one that is a second order. This is a first order. This is second order. This is maybe an 3 points. The second order. It is a first order. Sorry, and then it is the third order. Like this, you can go on increasing, and these are the points through which we can represent a rectangle. Okay. So there is one more element type is quadrilateral element. In this quadrilateral element, what it happens, the in rectangular element, in triangular element, you have a shape like this. Okay, but rectangular element, my size of the shape is like this. But most of the time, if you want to make certain surface or make some area, so your shape will not be in a fix. My area maybe I'm going to change it like this, anything. So, and maybe these lines are not parallel to each other. Maybe these lines are not parallel like this. So in that case, I need the flexibility in meshing it so that I can take in a complete area of rectangle, and that's what. So this type of element is defined. That is what is called as a quadrilateral. In this quadrilateral, the size of the each edge is not fixed. Also, it is not expected this edge and this edge are parallel to each other. This angle also I can vary it. So we'll look at this if I'm going to increase or decrease the angle, how the results are going to occur. That part we'll take into sometime later. And this quadrilateral element is most uh, applied to a real life situation, because in most of the cases, if I have some hole inside the plate, so I'm going to measure it. Obviously, this type of element will fit it perfectly. So if I'm going to measure it rectangular, what will happen? It will miss some of the areas, like this much part it will not measure. Only may create a more approximation, may not give a better accuracy. So in that case, this quadrilateral, this type of quadrilateral element, this will be much more helpful, and that's the reason this element is defined. If you look into this shape, if I'm going to, this is nothing but a curve, I need to model it. So this can be converted quite easily into a quadrilateral, and this will be, instead of curve, it will be kept in a straight line. Because that is what an approximation most of the time we do it. If you are taking a rectangular element, I have to take this much area and I have to leave this much area, so which is not representing in a geometry of that particular model, and it may affect your simulation. That's the reason this quadrilateral element is mostly used in 2D analysis. In this quadrilateral element will have a higher order. This is a first order. This is also first order. This is maybe in a second order. Second order. Likewise, if I go on increasing the nodal points on the edges or in between the area, or I'm going to increase the internal nodes into the element. So that will increase the polynomial order, and I can get a higher order polynomials, higher order elements into this. So we'll now look at what is meant by axis symmetry. Just consider this is nothing but a cylinder, and you apply the pressure on it. Okay, so pressure from inside, outside is atmosphere. When you are doing an analysis, so actually you are going to divide this into 3D element, and you want to do analysis. So in that case, what it happens? So when you are doing such analysis, it takes in a too much number of elements, too much number of nodes, and per node maybe in a six DOF. So obviously six equations, and it needs in a too much computational. To avoid this computational effort, so if I consider this is nothing but an axis, which entire model is symmetric. That's what it is called as an axis. So if I, this is nothing but a plane, this is one plane I can have. So similarly, I can have on another plane. So this may be in another plane. Okay. This may be in one more plane. Okay. So these are the planes on which if I go on determining the stresses, this may be in a one, two, three or something, these three planes. Okay. This is my second plane. This may be in a third plane. If I look at the values of the stresses in any of these three planes, I'll observe that value of the stress, maybe deformation, maybe a strain, are same at each and every location, in each and every plane also. So why cannot we do one thing instead of putting this entire 3D analysis? We'll convert that into a simple rectangular and which represents an axis of symmetry, and you're going to apply the pressure on this edge, and that is nothing but it is conversion of 3D model into an 2D axis. So that will help us to reduce only huge number of computational effort and also reduces the number of degrees of freedom. So that is what an advantage. And this type of axisymmetric modeling analysis is most useful in engine analysis, where we do maybe in a piston cylinder analysis you want to do, or pressure vessel analysis you want to do. Boiler is also mostly circular in shape. So that type of shapes you can use it. And we already had a discussion on plane stress and plane stress. So I will not continue that. You can just refer to the previous videos where this plane stress and plane strain is discussed in detail. So if you look into the 3D, three-dimensional element, okay, then this 3D dimensional element, just a minute. We have seen in a one 2D analysis, there is an element called as a quadrilateral. Here it is in a tetrahedron element, which will take care of any kind of an. That's what it is, a four-noded tetrahedron. It is like in a prism and can be used for analysis of it. So this tetrahedron will have only 4 points into the at its um, vertices and will have a lesser number of degrees of freedom. If I consider this as a single element into this, and if I'm going to have that is a brick element or rectangular prism element. So this takes on a two more number of equations. Here we'll have a one, two, three, four nodes, and each node is having a 6 degrees of freedom, 24 number of equations. Okay, in this case, and my stiffness matrix will become a 24 by 24 like this. If I consider this rectangular prism or brick element, we'll have a 4 and plus 4, 8 nodes, and each node is having a 6 degrees of freedom, then it becomes 48 number of equations, and your stiffness matrix is somewhere 48 by. So that is what most of the time it is preferred over that tetrahedron element is most useful, and also it takes in a very less number of equations or in a similar kind of an analysis. That's the reason tetrahedron is preferred more in case of 3D analysis. But sometimes when you can't mesh it and your shape is regular, and so you can go for Greek element. So there is one more element that's called as an hexadron element, where in brick element you can see this edge and this edge are parallel. These edges are parallel to each other, and but in hexadron, some of the shape you can't pop up into 3D element, and then that in that case you can keep that this there should not be any parallel edges. The size should not be restricted. Change that shape. That is what it's called as an hexadron. So if you want to increase the order of the 3D element, that is the three-dimensional element, you can go on increasing the node point between it. So this is nothing but a 3D element. So if I this is nothing but on one edge and this is entire edge, and we are going to put it one more node. So that's what it's called, a quadratic element, and we can use for an more accurate kind of an analysis. This quadratic. So similarly, if I want to increase the more one more order of the deformation, I can put one more node here. I will get in a cubic equation. So if I increase one more node, I will get in a fourth order equation and kind of. So when we are doing an entire analysis, there will be a certain convergence condition. Convergence means there is in a real life situation. Here it is in a real life situation. Okay? And you are done in some approximate analysis. Okay. So this approximate, if I take on a difference of these two, what are this difference? Should be minimum or it should be equal to 0. Okay. So then I can say what are the analysis I done at perfectly match with the real life. So to reduce this error, there are certain conditions we follow when we do machine maybe doing an analysis, and that conditions are called as the convergence condition. What you are going to converge, you started with an approximation. You have some real life situation, and you are moving from approximation to the real life. And during this conversion, you need to have a certain condition through which we that these conditions are called as a convergence. How this convergence condition will be useful? So first convergence condition, the function should be in a continuous and differential. Continuous, it is differentiable. So if I consider a 1D element, okay, in this 1D element, we assume that u is nothing but an a0 plus a1x. Okay. If I take a first derivative du by dx, it becomes an a1. If I take one more derivative du by dx, this becomes 0. So means this is not more differentiable. If I'm going for a higher and higher order for differentiation, what is going to happen? My derivative becoming a GU. It is anyway it is not acceptable, and that's what it is called as a discontinuous. And this type of discontinuous function will not be much more helpful when you are doing an want to satisfy condition higher order condition, and that's what your function should be in a continuous enough. And that continuous function is typically continuous function is the sin x, cos x. These are the functions which will be used for uh, analysis purpose, but in FEA these functions will not very less be applicable. We are only dealing with an only strain up to strain. That's what we mostly rely on this type of functions. If you want to have a higher order, like I want to also match this curvature. This is what it is called as curvature. Second derivative of displacement is called as curvature. Then this equation is not much more helpful. In that case, I need to consider quadratic equation, that is a with x plus a2 x squared. So that is what higher order I need to achieve. And this function should be in a first condition is a continuous within that particular domain. It should not be function like in a, so just take a simple example. If I consider one node here and another node here, okay, and I'm going to have a u1 displacement here and u2 displacement here. So this should be joined within a simple continuous variation. This is nothing but an a u. If my function is something maybe uh, maybe it is moving in this fashion. Suddenly it is increasing and suddenly it is decreasing in like this. This is what it is called as a discontinuous function. And this type of discontinuous function will lead to wrong answers or maybe create difficulty in simulation. So that's what this type of discontinuous functions should be avoided whenever it is possible. And also it should be differentiable. If I take a derivative of this particular function, I'll get in a single constant. That is what we call as a constant strain I will get. And that's what in triangular element also we assume constant strain triangle. And this is automatically satisfied within a polynomial function. What are the boundary conditions you're going to apply onto this should be satisfied with polynomial function. So second convergence criteria. So displacement polynomial should include in a constant term. So constant term means how this constant term will be in a help. Just look at this. I will just take one simple example of cantilever beam. If I'm going to apply this is nothing but my cantilever beam. I'm going to apply the force at this, and maybe this is my free end, and I'm going to apply the force at this point. I divided into number of elements. This is my one number, two number, three number, four number elements. 15 minutes. So if I apply the force onto this, what will happen? Hmm? So deformation in practically the deformation should be like this. If I doesn't take a constant term in the equation, what will happen? It will go on deforming up to this point, and this will deform in this fashion. So actually, this is nothing but a big deviation between these two. And if I consider in a constant term, my behavior will like this. And if I doesn't take in a consider this, then deformation will be like this. So this behavior, this is more realistic one, and that is what it is to be taken into account. And that's what whenever I'm assuming any polynomial, you maybe this constant term should be there, and if I'm not using this constant term, it will not take account of this rigid body deformation. This particular element is not deforming at all. It is only moving from one place to another place. This element will have a zero deformation, zero strain, stress, and all these things. Okay, but it should move, and that is what it is taken care by this constant term. And then that's what there should be one term into the polynomial that represents a rigid body displacement, and that's what the second condition should be satisfied whenever we are assuming these equation, polynomial equations. Okay. So third is there should be a linear term. Term. Polynomial will have an u is equal to a0 plus a1x plus a2x square. Just imagine this is a quadratic. In this case, if I miss this element, this particular term, then my equation becomes a0 plus a2x square. I not put this term. So what will happen? So this will not result into a constant strain with an element in some cases, and that may also lead to a wrong result. And that's what we should have a linear term. Linear term means this within a power of one, x in power of one, or kind of. And if you miss this, obviously you are going to miss this constant strain in the element, which may happen in certain cases practically. And that also will be taken into account. So that's what this third convergence criteria should be. There should be a linear term all the time. First convergence criteria is continuous in the function. Second convergence criteria, there should be a constant term in the polynomial. Third convergence criteria, there should be a linear term in it. If I'm not taking into linear term into account, obviously I can't get in a condition in the simulation where I can have a constant strain in the element, and that may will that is not in more realistic way it is happening. So then fourth condition, compatibility. Compatibility means what is going to happen. So if I consider one element, and this is my second element and this is my third element. So this is nothing but a node where I have a common point. This is my first element and second element. So if I take a separate element analysis, I got an U1 as a deformation here and U2 as a deformation. Similarly, if I take separately that second element, here it is my U2 on second element and U3 on second element like this. This U2 on first element and this U2 on second element, these two values, this and this should be equal. If they are not equal, then it is called as an this will now lead to a deformation. This element will deform. So this, and suddenly it will show on a sudden change into this. This will not see, and another deformation. This sort of gap you can observe, and this gap is called as this is due to an incompatibility in means that's the reason when we mesh it or we create an assembly of the stiffness matrix. Okay, we take care of in this uniform deformation in the both element. This and this will be the same, and that's what we add these equations of matrices, and we get in a sum. We will have in a sum terms will get added up, and maybe at an diagonal location. So this is what it is called as a compatibility. So here, what kind of a compatibility we are going to provide? It is in a displacement is uniform over the elemental change. That's what is called as a displacement. And here it is a displacement is termed as u. And derivative of this is a zeroth derivative. Zeroth derivative. And that is what it is called as a C0 type of compatibility. C0 type of compatibility. Okay. And then if I consider another one, that is the beam type of an element. If I consider in a beam type of element, maybe in this type of element, I fixed it here and I'm going to apply the force at this point. So these elements will go on rotating it. It will create a deformation pattern in this fashion. Okay. So if this is nothing but a one element, and this is my second element, and then my third element. If I consider a graph of this deformation graph will be like this. This is my first deformation, then second deformation, then third deformation. Slope of whatever this curve may be there. There is slope of this particular curve at this point, and slope of this curve on this point. Then in the first element and second element should match. This is slope in first element, slope in second element. If these two are equal, then it is called as a C1 type of continuity. Why it is called as a C1? Because displacement represents u, strain or slope represent du by dx, and that's what it is called as you are taking in a first derivative, and that is a first derivative, and that's what it is called as C1 type of compatibility. Okay? And once we achieve the C1 type of compatibility, so some of the cases with that where we may be needing a C2 type of compatibility, that is higher order. That is what on a plate type of. If my plate is like this, and I'm going to apply the force. So this plate may go on deforming like this. Okay? This plate is going to deform in this fashion, and when it is going to deform, whatever the tangent or whatever the derivative, first is u is C0 type of compatibility. Du by dx is my C1 type of compatibility, and d2u by dx square or d2u by dx and dy. So these two type of, because it is order of the polynomial, that is derivative, is at second, that's what is called C2. Each should be satisfied to, whenever you are going to move it from one element to another element. And that's what this is C0 type of compatibility, C1 type and C2. Whenever you are doing in a plate type of analysis, you are going to. So then last condition, that is polynomial shall satisfy geometric isotropy. Geometric isotropy means you whatever the material you are assuming it is isotropic in all the directions, its properties. So that also to be taken into account. Otherwise, different user analyzing the same component may get different result by following different node number sequence. And if I'm going to change in a node number sequence, also I will get a different results. That's what it should take account of geometric. And these are the five convergence criteria. Minimum five convergence. There may be no more convergence criteria also will, but these are the basic convergence criteria should be satisfied whenever we are going to model, if any model. So this is for today's session, and thank you all. Thank you very much, and